So moving in the same direction, now we are going to move. Okay, aperiodic signal, periodic signals we have also defined in the last lecture. So today we are moving with energy and power signal and some examples of energy and power signal, right? So I'm going to start the session of today. Okay, so last time we have discussed about the energy and power signal, and with is it visible to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So we have defined the energy and power signal, and here we have discussed that the energy signal is a signal for which the energy is a finite. So if we consider the energy is the area under the curve g of t whole square. Why we are using absolute value? Because some signals are all g of t signals are not a real signal. Some g of t signals are complex signal. So it may be this is applicable to a real signal as well as the complex signal, right? So that's why we are using a absolute value of g of t. Absolute value of g of t will gives the same value for a real signal, but for complex value it gives a magnitude of signal, or consider only absolute value, a real part of that one. So this absolute value of g of t whole square, and if we integrate this for whole duration of the signal, then it is known as the area under the curve absolute value of g of t whole square, and this is simply known as the energy of the signal. So energy of the signal is basically considered as the area under the curve g of t, absolute value of g of t whole square, and the signal which is known as energy signal if it energy is finite, if it has a finite energy. So for this finite energy, we can have mention the condition that if your energy is belongs to or it falls between 0 to infinity, right? So then the energy is considered as a finite energy, and the signal is known as a energy signal for the same, right? But this signal which is known as energy signal is applicable only for the case if the signal has a finite duration. And how we can say the signal has a finite duration? So if any signal is start from somewhere and ending from somewhere, so we can say the signal has a finite duration. So for such kind of a signal, we can say if our t is the time approach to infinity and amplitude approach to zero, right? As the time approach to infinity and amplitude approach to zero, so we can say that signal is of a finite duration, and for every finite duration signal we can find the finite energy, and this signal is known as a energy signal. So one conditions that we have already mentioned earlier is the energy signal has a finite energy. If any signals has an infinite energy, it should not be considered as a energy signal, right? So now we have taken one example. In this example we have considered this, and this signal is approaching to infinity, is exponentially increasing. So we can say as the t approach to infinity, amplitude a also approach to infinity, so that doesn't belongs to energy signal because it doesn't have a finite energy. Now consider to the second signal g2 of t, we can say as the time approach to zero, the amplitude approach to as the time approach to infinity, the amplitude approach to zero. So this signal is known as a energy signal because it has a finite energy. Now moving further, we have described that the periodic signal is a signal which repeats itself after some time. So cycle by cycle its pattern does repeat. So such kind of a periodic signal is basically start from minus infinity and approach to plus infinity, right? And from where you can start the cycle? So cycle you can start from any of the points, and if after repeating, if you return back to the same point, so one cycle is to be completed. So very interesting property of the periodic signal is that you can start the cycles from anywhere, right? Any points, and when you return back to the same point, so one cycle is to be complete. So for a periodic kind of a signal, they just basically start from minus infinity to plus infinity, and such kind of a signal doesn't falls in the category of energy signal, because if we find the energy for whole duration, so energy becomes a infinite. If we find the energy for every cycle, and energy for first cycle is easy 1, energy for second cycle is easy 2, and consecutively we can find the energy for all the cycles. So energy for one cycle may be a finite, energy for second cycle may also be equal or finite. But if we consider energy for all, then finally there are infinite number of cycles that's present. So we can have a finite numbers are added for infinite times, it becomes infinite, right? So that's why the energy is infinite for any periodic signal. So for periodic signal, energy doesn't measure, right? So what is the measure for here? So for such kind of a cases, we can find the power of the signal, and power is considered as the energy consumption or energy per time duration. So energy per time duration is considered as a power. So the we can define the power signal P as a limit t approach to infinity. It shows the total time duration of a signal is infinity, and rather than to finding the energy for whole duration, it's a better we can find the energy for one cycle and divide it by the time period, because after it all it gives the same thing, right? If we divide the total time duration with n cycles, so we are getting the energy per unit times, or we are finding the energy per cycle and divided by the duration of cycle, that also gives us the energy per unit time. So if we normalize this area with 1 by t0, 1 by t0 is the time period for one cycle, and if you find the energy for the duration of 0 to 20 means for one cycle, right? This is for one cycle because it's a periodic signal. So whatever the patterns are in one cycle, they are repeated. So if you find the energy for one cycle as a g of t whole square, so this is the energy per cycle and divided by the time period 1 by t0. So that gives us a power, and we are assuming this the signal is a periodic in nature. Not necessarily all the signals are periodic in nature. So we can find some signals which are a random signal or noise signal which doesn't show any pattern. For that kind of signal also, the power is a true measure. So what is the unit of energy? So energy, the unit of energy can be considered as a joule, right? And what is the power? So power is considered as a the unit of power is known as a watt, and 1 watt is equal to 1 watt is equal to 1 joule, uh, 1 joule divided by the second. So joule per second is known as a watt. So that is the relationship between energy and power. And then we have described that energy and powers are tugging the war together in opposite directions. So if any signals is either energy signal is never before is a power signal, and if any signal is a power signal, so it has infinite energy, so it never be a energy signal. So we can define. Yes. Hello. All the students are requested to keep their microphone off. Any signal which is energy and power both, there is no any signal which is energy there is no any signal which is energy and power signal both, right? So signal may be either energy signal or power signal, or there are some signal exist which are neither energy signal and nor power signal. So this part we have already covered, and that we have already discussed about the energy signal as exponentially decreasing function that falls as energy signals. uh, the energy signal, the second energy signal is we have defined as a rectangular function and exponentially decreasing function. This is also of a finite duration, start from somewhere and ending from somewhere. And the rectangular signals we can even define as a energy signal. Right, so these are the examples of energy signal. Then we have described the power signal. So any signal which is periodic in nature, that is known as a power signal. Then we have described any noise which are not exactly periodic, but it even start from minus infinity to plus infinity, and some quantity of them are periodic. Right? If you find autocorrelation function and other quantity, average values of the signal, that is periodic. So this signal also falls. This is known as a noise. Noise is a totally random in nature, and this noise does also falls in a category of a power signal. We have even given one examples in which some signals are neither energy or power signal, like as exponentially increasing function. U of t unit step function is also increasing continuously, so it does also falls in the category of neither energy nor power signal. Now Now it is a time for some example. So if I just throw some examples in front of you, so you can have idea how to calculate the energy and power of the signal. So first thing is that you need to determine suitable measure of the signal, measure of signal, right? For which kind of a signals we will have to find the suitable measure. So let's assume this is a signal -1 0, and that's amplitude is 2, right? And it's exponentially decreasing. It's exponentially decreasing. Its amplitude is 2, and this exponentially decreasing function is 2 into e raised to minus t half. I hope everything is visible to you, and my voice is even audible, right? If you find any trouble in between, you just let me know, because sometimes connection may be lost, and sometimes from my side I may be enter in some other format, and so maybe possible you are not getting the connections, and visuality is not clear. So you let me know. I will just make some corrections from my end, or I may repeat from somewhere where the something has been left. So this is one signal. The signal is given, and this is the first signal which is given, and the second signal in which is given over here is like this one. Now we can have to measure. Sorry. This is the another kind of a signal. This is another kind of a signal, right? And this signal is 0 to 1, and here it is 3, -1. The amplitude is 1 and -1, right? We consider this first signal is a G1 of t signal, and the second signal it is continuously forever in both the direction, and the second signal is G2 of t signal, right? Now you have to measure the suitable measure. I mean, first you let me know what about the first signal. What is the true measure? From energy or power? This first signal is energy signal or power signal? We can start with the first. The solution will for a first signal, right? So what's about this signal? The signals I again draw over here. You let me know, is it e raised to minus t? This is the 2. Its amplitude is 2, and this is -1 0, and that is t. Now you let me know whether this signal is energy signal or power signal.
Energy signal.
Energy, right? Energy signal, right? Why so one condition we need to check is, as the t approach to infinity, the amplitude approach to infinity, sorry, amplitude approach to 0, right? And that is known as a finite duration signal. So what we can say here, this is the fix, this portion is fixed, right? To it's known as a rectangular function. But so that is obviously finite duration, because this rectangular does exist from -1 to 0 only. But if we see the another portion, 2 into e raised to minus t half, so in 2 into e raised to minus t half, if we can say t approach to infinity. So what happens? 2 into e raised to minus infinity. And e raised to minus infinity does 0. So this signal amplitude does goes to 0. So we can say this signal is of a finite duration signal. It starts from somewhere and ending from somewhere. Now, how to represent the signal mathematically? So G1 of t we can represent. This is the constant amplitude or rectangular function from -1 half to 0. So we can define by the constant amplitude too, because it's a rectangular function over there. But from other duration, from 0 to infinity, this signal is exponential signal with the amplitude 2 into e raised to minus 2 half. Why it is 2 into e raised to minus t half? Because if we put t is equal to 0, then e raised to 0 becomes a 1. So we get the amplitude 2 over here. Right? So it is known as a 2 into e raised to minus t half. So this is the signal. So signal can be described in a two parts. The first part, in which the signal is a rectangular function. It is from -1 to 0, and for other duration over which the signal is exponential signal, it is from all the duration from 0 to infinity, right? Now we have to find the energy, because we have already defined this is the energy signal, right? we have defined this signal is known as energy signal. So we follow the equation of energy signal. So for energy, we have to find this is of whole duration energy of any signal, that's from minus infinity to infinity g of t whole square dt. This is the equation by which we can find the energy signal. Now, for this signal, we can say this signal how you define. So this signal can be defined in two parts. We don't have any value from minus infinity to minus 1, right? So the first lower limit is minus 1. Then we can define this is from minus 1 to infinity. Infinity g of t whole square dt. But from minus 1 to infinity also, signal is comprised in the two parts. The first part is this portion. This is known as a rectangular function. And the second portion is this portion, which is known as the exponential function. So we need to integrate this one in a two part. For the first part, we can define this signal does exist as a rectangular. We will follow this function for minus 1 half 0, right? We will follow this function g dt, and for another half means this one from 0 to infinity. 0 to infinity, we will follow this function, right? And we will put all this value there. So that is minus 1 to 0. The function is has a plus 2 amplitude. So we can have this a plus 2 whole square dt. For another half, 0 to infinity, this one is a 2 into e raised to minus t half whole square dt, right? This is like that. Now, so if we integrate this one, we can say it is minus 1 to 0, its value is 4, and from 0 to infinity, its value is 4 into e raised to minus t half square. So it is e raised to minus t dt, right? Now we simply take the integration to find the energy. So 4 multiply with the t, because integration of 4 is 4 into t, and that is of minus 1 to 0 are the limit. And for this 4 into e raised to, so that becomes a minus 4 into e raised to minus t half, right? Because e raised to minus t means it's a minus e raised to at is a time e raised to at, but a is minus 1 here, so it is minus 1 time e raised to minus t, and 4 is already there. So then we gives this value 0 to infinity, and now we will apply some limit, right? So we will apply this limit 4 and 0 minus 4 and minus 1. This is given in the for a first integration. For second integration, we can say minus 4 into e raised to minus infinity minus minus plus, right? So 4 into e raised to 0. So if we solve this equation, so we are getting here 0 plus 4, and here we are getting the as a minus 4 e raised to minus infinity is a 0, right? So this one is a sorry, this one is a 0. So here we can say the first term would becomes a 0, but the second term would be a 4. So that would be a 4 plus 4, and that is 8. So what is the 8 joule, or we can simply say is equal to 8 joule. So what is the energy of the first signal that we have found is a 8 joule, right? So that is done. Now we go for second one. Now you let me know. I redraw over here in a solution. I redraw the same signal. So if I redraw the signal over here, so this signal does exist from uh, in this form as a ramp signal, right? This signal is a ramp signal. And what is the value? What are the values are there? 0. This one is the 1, and this lower limit is a minus 1, right? And you can pick up any of the cycle. So minus 1 to 0, that is 1, and that is 3. You pick up any of the cycle, huh? You can start from 0 or somewhere, any of the cycles. But I would like to pick up this cycle from minus 1 to plus 1, right? So this is the time duration. So what is the time duration over here? So time duration is known as a 2. Now, how you define the signal, right? This is the case. So first, let me know whether this signal is a energy signal or power signal. So we are assuming this is starting from minus infinity and approach to plus infinity. So that is example of power signal, because it's a periodic kind of a signals, and for periodic kind of a signal, they have an infinite number of cycles are there, and for every cycles the energy is a finite. Then infinite times you add that finite number, that becomes a infinite again. So this signal is just is an example of a power signal. So we need to find the power. So what is the time duration of this signal? t0 is a 2. And how you define this signal? So g of t is basically defined as a slope multiplied by t. It's like a ramp signal, slope into t. But what is the slope? So slope is simple, defined as a y2 minus y1 divided by x2 minus x1. Right, this way you define, multiply with the t. Now what is x1 y1 and what is x2 y2? So x1 y1 is just to define your first point, right? So this point here, this minus 1, at this point we have to define it. This point is x1 y1 because this is positive going 10, and here the slope will over, right? So slope will start basically from here, right, and it will be ended over here. So this point is x2 y2, sorry, so point number 1 and point number 2 you need to connect. And so what is x1 y1 here? X1 y1, right? So what is the value of x1 y1? X1 means x-axis value, so that is minus 1. And what is y1 here? Y1 is minus 1. Is a y-axis value, this one. And at this point, what is x-axis value? 1. And what is y-axis value? 2. So x2 y2 is basically known as a 1 1 again, right? So it's a minus 1 1 minus 1 minus 1, and x2 y2 is 1 1. So now we have to find the slope y2 minus y1. So y2 is 1, right? And what is x? This y2 is 1, and what is x2? Sorry, y1. Y1 is minus 1. So minus minus 1, right? And what is x2? So x2 is again 1, and what is x1? X1 is minus 1. So that is of minus 1. Multiply with the t. And if you take 1 minus minus 1, so it is 2. 1 minus minus 1, 2 into t. 2 2 will be cancelled out. So finally you are getting g2 of t equal to t, right? This is not a case always. If the slope is different, so t is multiplied with some constant value like as a 2 3, depends on the slope. But now we have found that this is the actual equations that we will follow for our further analysis, or sorry, further calculation of a power signal. So now what we can derive here, our signal G2 of t is equal to t for how much duration? So for one cycle. So if you are considering this cycle is from minus 1 to 1, so we can say it is for every cycle, that is 1. So it is from minus 1 to 1. It is from minus 1 to 1. Now we will find the power of the signal. So if you find the power of the signal, so power is basically defined as a total duration of signal is suppose t approach to infinity. This t0 is the duration for a one cycle, and this is the integration limit is for one cycle. We are finding the energy for one cycle, so it is 0 to t0 g of t whole square dt. So it's not g, it's our g2, right? Because signal is g2. So we can say now I omit this one because everybody understand this one, that the total duration of this signal is infinity. So it's there is no need to use it in every calculation, right? So better, or if you want to carry forward, you can carry forward. Otherwise, you can omit this. If t doesn't comes in your equation, then you omit this, right? So finally, our equations after omitting this for a simplified case, after for a simplified equation of this one is 1 by t0, 0 to t0, g2 of t whole square dt, right? G2 of t whole square dt. And if you find 1 by t0, the g2 of t is what? T, right? So I place this as a t square, actually the absolute value of t square or t square directly. So that is what 1 by t0, t is itself considered as a real number, so that becomes absolute value itself becomes a t. That is the t square by dt. Now if you take the integration, so it is the tq by 3. Sorry, I may just write here minus 1 to 1. This is a good assumption. Either you can have a 0 to t0, or you can start from any other limit, minus 1 to 1. I put this limit over here, minus 1 to 1 we are considering. So for every places, I just use this limit minus 1 to 1. Starting of cycle and ending of cycle. So here also we are putting the same value, minus 1 to 1. Right? So what happens here? tq by 3 minus 1 to 1. And what is t0? So t0 we have already identified earlier. t0 is the value of one cycle, that is 2. So we can say 1 by 2. And that's why we can say 1 by 2, 1 First we apply this limit 1, so 1 by 3 minus 1 uh, by minus 1 q, right? So if we apply this limit, so that becomes a minus 1 q by 3, right? So if you solve this equation, so it's a 1 by 2 1 by 3 plus 1 by 3. 1 by 2 is a common, and if you cancel out the common terms over here, so it is a 1 by 3. So what is the power that we have found is a 1 by 3. This is the power we have identified. So power here is a 1 by 3 watt. Okay, fine. So this is known as a power, and what is the power you have found as a 1 by 3 watt. Now I would like to give you some example for your later study. That is work like as your exercise, right? Work like as your home exercise, and whenever you come with the solution in the next lecture, we will discuss in a more detail. So there are some exercise. Find. Okay, now there is another thing is RMS value. So we simply, if we talk about the RMS value, it's known as a root mean square value. So RMS value is nothing else, but it is the square root of power. It's a square root of your power. Right. So here we will take some examples as your home exercise. Three examples I will give you, and I will even give you the answer so you can check it out at your home. The first example is the g of t is c time cos omega 0 t plus theta. B is where the signal g of t is equal to c1 cos omega 1 t plus theta 1 plus c2 cos omega 2t plus theta 2. This one is your second example, right? And give you the third example is a C, that is d g of t is equal to d time e raised to j omega 0 t, e raised to j omega 0 t, right? This one is there. So there are three examples, and you have to solve this example as your home exercise. You can note down here. We will stop for 1 minute, so you can note down this one, and then we will go with some very useful property of the signal. We will go with some very useful property of the signal. Okay. Okay, so I hope you solve this example at your home. The answer, I would like to provide you the answer. The answer of the first A is c square by 2, right? Answer of B is c1 square by 2 plus c2 square by 2. And the answer of the third one is home exercise. Home exercise, find power and RMS value of signal, right? You have to find the power and RMS value of the given signal. Three signals are given. So the answer is c square by 2 is the right. This is again a power. So RMS value is simple square root. So I am not writing here. Okay, let me write. So it becomes a c square by 2 like that. And same for here. And the answer of C is D, absolute value of D. Right? So this is the power of first, second, and third signals. You can note it down. So I will rub out, and then we will go with some another property of the signal. Okay, so I hope you have noted down. So now we will move to the another things about how to manipulate. Okay, so let's start with Now we will discuss about some useful property of the signal, right? We will see some useful property of the signal, and this property is very helpful because once we start to learn about some new things, right? So this useful properties, these properties are very useful, right? So very useful properties that we are going to learn. So first property under this category is known as a time shifting property. This is very interesting property that we are going to learn. This is known as a time shifting property. Right? So for every now what we can say, this time shifting property means if the signal is advanced by some amount of time, or it may be delayed by some amount of time, right? So how we can represent this signal? Okay, so this is interesting property because event maybe happens at some times, and we want to see how the signal will be responded after some time. Like for example, if you are transmitting something from your transmitter, so not necessary quickly or the same instant it will reach to receiver. It will reach to receiver after some delay, right? So what happens with the signals and how the signal can be represented in such kind of a things? That is very interesting to learn, and that we are going to learn in this time shifting property. So if you shift the signal either right side or left side, or maybe in advance of the time or delay of the time, so how we represent the signal, that we need to understand. The another thing is a time scaling property. Right. So the time scaling property will define if you are doing some scaling on the time axis. So all these properties are related with the time axis. So this time scaling property will tell us if we compress the signal or if we expand the signal in a time axis, then how it can be represented mathematically. And the third is known as a time reversal property, right? So if we shift the signal from positive to negative side or negative to positive side, I mean we reverse this the signal with respect to the zero axis or vertical axis, right? We flip the signal from either right side or left side. So how the signal can be presented. So these are very useful property, and that we are going to learn this property today. We will can have some more examples and all these things. We will address at later stage. But today we just discuss about some useful property of the signal. So first property that we are going to learn today is known as a time shifting property. Assume you have a signal like this, right? You have a signal like this one, and this signal is simply defined as a g of t signal, right? This is the g of t signal. It's a -1, and this amplitude is 1. Now, if you shift the signal right side, if you shift the signal right side, so I can say this signal is shifted right side uh, with respect to this one, like here. Uh, Rather than what is the where the signal does actually present a middle point 0, right? The signal does present at a 0. Now I shift the signal to some other value like a rate. So this whole signal will shifted here. This is 0 to -1. So now this is if 2, then this becomes a 1, right? And this point is becomes a 3, right? And then one this signal can be represented as this. So how you represent the signal? So this signal is considered as a delay, right? This signal is considered as a delay. By how much amount you have delay? So initially the middle point at 0, right? And now the middle point is 2. So this signal is delay by the amount of 2, right? So this can be represented. Delay is always represented with a negative sign. It always represented with a negative sign. So we can say this signal is a delay by some amount. How much amount? 0. So what we can put over here? This is the negative. It means signal g of t is a delay by how much amount? To some amount t0 is equal to 2, right? Some amount by delay by some amount 2. So this is the represent by the negative sign. Negative sign, right? It's like as somebody will start their morning from 6 o'clock, and somebody may start some morning by 8 o'clock. So you can say the person who has started their morning or their day by 8 o'clock is just 2 hours delay by the person who has started at 6 o'clock. So that is defined by the negative sign. Keep this thing in mind. The delay of signal is always represented by the negative sign. Now, contradictory to this one, if some signal are shifted, if I draw, these signals are shifted 2 point right side. This one is a left shifted, right shifted. This one is known as a right shifted. But if the some signals are left shifted, right? Like some person will start their morning from 6 o'clock and some other person start their morning from 4 o'clock. So relative to the 6 o'clock, the persons who start their morning at 4 o'clock is considered as advanced by 2 hours, right? So this advance will represent by the positive sign. So if we shift the signal from 0 to -2, this point is now -2. This point -1 point is now becomes a -3 point, and this one becomes a -1 point. Yes, it becomes a -1, right? And you can represent the signal like this one, right? So this is the same signal. So how you represent this signal with respect to g of t? So this signal is advanced by time period 2. So we can represent is a t plus 2. Is a t plus 2. And how we represent the signal is a g of t is advanced. We can say it is advanced by some time amount 2, right? And that is represented here with the positive sign, right? And where the signal is actually shifted left side, so this is known as left shifted signal, right? So this is very interesting property, and this property is just to define whether the signals are right shifted means delay, or maybe left shifted means advance. How much time amount it is right shifted, it is defined by minus sign, and how much amount of the signal is shifted left side, it is defined by positive sign, plus sign. Okay, so I think you understand this. Okay, now we come to the next property of the signal, and this is the time scaling property. This is known as a time scaling property. So the time scaling property is basically defined as a two-part. Time is reduced. Time duration of the signal is either reduced or expanded, right? So that is either we can say the signal is compressed or signal may be expanded by some factor. Expanded by some factor. For an example, if I have a one signal, this signal is I can define this signal as a original signal, right? An original signal is like as this triangular signal, and for this signal it does exist from some value of minus t to plus t, right? Plus t, maybe capital T would be any values. It may be minus t to plus t, and it has some amplitude of 1, right? Now if I compress the signal by some factor 2, if the signal is compressed by factor 2, right? So how you can see compressed by factor 2 means not amplitude, huh? Not this, all these properties are applicable to the time axis, so we are not talking anything about the amplitude. So compressed by the factor 2, it means that this time axis is compressed by factor 2. So whatever the points which are earlier available at minus t is now shifted to minus t half, and whatever the point which are earlier, which is earlier at capital T is now at a t half. So you can say the signal is thus compressed, right? Whatever the signal durations is now reduced from 2t to 2t. So that signal does compress, and after the compressing, we can say this point is now minus t half. I will show in real compression. So that is like this one. This is compressed. This is compressed, right? And after compression, you are getting the new point as a minus t half and t half. And if this is my signal g of t, so how we represent this signal which is compressed by factor 2? How we can represent? So if any signal is compressed by factor 2, we can represent as a g of 2t. G of 2t. Why? Where 2 is what? This is known as a compression factor. Now you may surprise, we are multiplying with 2, so how it is compressed? So basically, this is with reference to this time axis, right? So it shows whatever the value earlier case, if in earlier case whatever the value which is available at minus t, now it is available at minus t half. So in this t, if I put minus t half, then 2 will be cancelled and I will get the value of t. I just to show you. Let's say this is a time instant, right? This is a time instant. So at minus t half, what is the actual value of g of t? What is the actual value of g of t? 0, right? It is here. And at the value of 0, what is the peak value? G of t is 1. And what is the value of g of t at again t half? Sorry, t. This is not t half. Sorry, at t, right? This is the, and what is the value of g of t at this point is 0. Now if we talk about the g of 2t, right, the same value available at 0 1 and 0, but not at this time instant. At which time instant now? This is available at t is equal to minus t half. This is available at t is equal to 0, and this is available as t is equal to t half. So it shows that if this t are put here minus t half, so you are getting the same value of 0 in g of 2t, which you have already obtained at g of t. It indicates this thing, right? The same for 0. If I put 0, so that becomes a g of 0, right? And if I put t is equal to t by 2 here, if I put this one, t is equal to t by 2, so it's a 2t multiplied by 2t multiplied by t half. 2 cancels, right? So sorry, 2. So it will give us a, sorry, 2 t by 2 right, 2 cancel, so it will give us the value of g of t at t half, right? I think you get this. So that indicate whatever the actual value that we have got earlier at the t minus t, the same value we are getting here if we put t is equal to minus t half. And whatever the value we have got at g of capital T, we are getting the same value if we put this small t is equal to t half. It means this is the scaling factor. So this one is known as a scaling factor. G of 2t is known as a scaling factor. So if you are multiplying with some value of a capital, here our scaling factor here is 2. Scaling factor is 2, right? A is equal to 2. So if you are multiplying the signal with 2, it means you are compressed by the same factor 2. And now if I expand the signal by factor 2, expand by factor 2, that means I expand the signal by factor 2. So earlier which value is available at minus 2, now we are getting at the same value of a minus 2t. 0 value are also multiplied with the 2, it remains same 0, but this value of t is again multiplied with the 2t. So now the signal does expanded from minus 2t to plus 2t, and this is expanding by some factor that can be defined by g of 2t. It means whatever the earlier value of g of minus t we can obtain if we are to put t is equal to minus 2t over here. So 2 will be cancelled and we are getting the same value of g of minus t. So that's why it is divided by 2, right? So this means this is the, what is the compression factor? So this is 1/2 is our this one is known as a, as what is the expansion factor? So this 2 is our expansion factor, right? Expansion factor. It simple means the signal is expanded. The signal is expanded by factor E is equal to 2. I think you got this one. So we can have two things: compression of the signals. If we divide the signals, if we expand the signals, that is known as a divided by the signals, and if we compress the signal, we have to multiply the g of with t. So now we can say if any signal g of at, right, how you define this is compress or this is expand? So if the value of a is greater than 1, if greater than 1, so it means simple, it is multiply. That means this is the operation of a compression. This is known as a compression of the signal. This is compression of the signal, right? And if for any signal g of t, if we say a is less than 1, then that is known as a expansion of the signal, right? For an example, if I say g of 3t, so that means the signal is compressed by a is equal to 3, right? And if I say the g of point point 2t, that does mean here we can say a is less than 1, so it is expanded by how much factor? So it is expansion, so that means it is represented as a g of t by 5, because point 2 is 1 by 5, right? So that means it is known as an expansion, right, by a is equal to 5. So that way you can have a compression and expansion of the signal. Okay. Now we will move to the last property of the signal, and this is known as a time reversal property. Time reversal property. So if any signal is flipped over the y-axis, right, like this one, there is a signal which does exist from 1 to 3, right, g of t. And if I flip this signal over this axis, y-axis, here, I flip this one, I flip this portion here, right? Then it becomes like this, -3, -1, and maybe somewhere. So if I say it is my G2 of T signal, so it is simply of G of minus T signal, or I simply define is as a G of minus T signal. It simply tells us whatever the value that of amplitude that we have achieved at +3, now the same value we can achieve at -3. Whatever the value we have already achieved at +2, that now we are getting at -2, that is the peak value. And whatever the values we have, or whatever the values of amplitude at t is equal to 1, now we are getting at t is equal to -1. So that way it is represented as a flip of the signal, right? I give you one more example before we conclude this session over here. If your signal will be like this, right, this is our signal, this is our g of t, right? So how this one is, suppose -3, that is 2 -2, and that is 1, right? Now you have to apply the time reversal operation on this one. So if any signal is right side, it may be flipped to the left side, and the signal which is on the left side, it can be turned to the right side. So after flipping, what we are getting here, this -3, the point which is available at -3 is, it should be now available at 3. The point which is available at -2, it should be available at 2 +2, and this point should be available at 1. So we can say the slope is from -3 to -2. There's all these values. Now we are getting from -3 to +3 to +2, and those -2 to -1 we are getting here as a. So this one is an example of g of -t, right? So I think that is sufficient for you to understand. So now look around to this. We have learned about the three operation. One is the time shifting operation, in which the signals are shifted right side or left side. If the signals are shifted right side, it is known as the signal is delay. If the signals are shifted left side, it is known as advance signal. The delay is always defined by negative sign, and advance is defined by the positive sign. The time scaling operations. This is the operation in which the signal is scaled by the some time factor. If the signal is compressed by some time factor, so it is multiplied with the t, and if it is signal is expanded by some factor, it is divided by the t. So in the case of g of at, if a is greater than 1, we can say the signal is compressed, and if the g of at, if a is less than 1 means I am not talking about negative, huh? It's always between 0 to 1. So if a is less than 1, it is known as a signal is compressed by some factor 1 by a. Expanded by some factor 1 by a, right? Then we have discussed about the time reversal property. In the reverse property, the signal says flip over from right to left side and left to right side. So that is the, after applying the flip operations, g of t can be concluded as a g of minus t. g of t is concluded as a g of minus t. So I think we need to stop over here, and because the time will not permit us to move further. But in next lecture, we will discuss more detail regarding the same. I hope you have enjoyed the session. And now just give me one more minute. So I will take your presence from my desktop PC. And I disconnect from here and connect with my desktop PC to take your presence. Right.